Welcome to the first unit of the training course. I'll use this lecture to discuss about the theoretical foundation of a land carbon cycle and a matrix approach. As you may have already known, I'm a professor from Cornell University. During the opening meeting, I have already mentioned to you that we have worked on a matrix equation for more than 10 years. We have found that a relatively simple matrix equation, as written on these slides, can unify land carbon cycle models, accelerate computational efficiency for spin-up, diagnose model performance with new analytics, enable data assimilation with complex models, and guide carbon cycle research with a new theoretical framework. Now let me explain why it is theoretically possible to unify land carbon cycle model with one relatively simple matrix equation. First, let's look at one pretty photo, which was taken several years ago in an island off East China. The photo shows that vegetation takes over abandoned houses and land after humans left the place. What would happen to the place in 10, 20, or 30 years? It is likely that trees will take over the place to form a forest. From a carbon cycle perspective, ecosystem carbon cycle converges towards an attractor state after human disturbance are removed. Here is another striking photo, a highly commercialized, heavily human-disturbed Manhattan, New York City. Let's imagine what will happen to the place if we could magically remove humans from this area for 300 years. What do you think would occupy this place in 5, 10, 20, 50, 10, or 300 years without a human disturbance? We would probably see small trees from the crack of concrete in 5 years. By 50 years, most of the high-rise would collapse and the forest will take over. In 300 years, it is most likely to be occupied by deciduous forests like this on this photo. Without a human disturbance, this place would converge towards the deciduous forest. This convergence of carbon cycle is totally done by Mother Nature. Here is a photo of Lujiazui, a commercialized district of Shanghai, China. Very glamorous. It would most likely to be occupied by wetlands or lowland forest in 300 years without human occupation. This convergence of land ecosystems also occurs during forest succession. The succession has been extensively studied. The past study has mainly been focused on species dynamic and community structure change. It has not been much done from perspective of land carbon cycle. During the forest succession, the carbon cycle converges towards some attractor. Scientifically, this convergence done by Mother Nature is actually the internal process of a land carbon cycle. Then, what are those internal processes? How can we mathematically represent those internal carbon cycle processes? Before we can answer those questions, let's briefly review land carbon cycle first. Carbon enters an ecosystem via photosynthesis. Photosynthetic products are partially allocated for autotrophic respiration, partly for growth of leaves, stem, roots. Once a plant or its part dies, they become little falls down to the little pool. Little decomposed, partly released to the atmosphere by heterotrophic respiration, partly incorporated into soil to become soil organic matter. Soil organic matter goes through decomposition and stabilization over and again, forming soil carbon cycle. We will examine some of the processes to see what the best equation would be to represent them. Let's look at another beautiful photo. This photo shows dead leaves were falling from the tree canopy to the ground. Scientifically, we call it litterfall. To make it a subjective study, we define two new terms, donor pool and the recipient pool. The donor pool donates little while recipient pools receive little. Litterfall is a rate process that moves carbon from donor pool to the recipient pool. In this case, the rate of little falling is proportional to the amount of little in the donor pool, where the amount of little in the recipient pool has nothing to do with the rate of litterfall at all. So mathematically, the rate of litterfall, denoted by dx over dt, equals to the donor pool size times a coefficient. This equation describes the donor pool dominated carbon transfer. Litterfall in the real world is affected by wind and the other environmental conditions over seasons. Modelers usually use an environmental scalar, Xc, to account for the effects of phenology, wind, and other environmental factors on litterfall. Once litter is falling on the ground, litter decomposes. Litter decomposition is usually studied with litter bags or wood log on the ground or in air. Litter decomposition is often described by the same donor pool dominated carbon transfer equations. K is often called litter decay constant. Actually, K varies with the type of litter and the location. This is a typical data set of litter decomposition. Researchers initiate a study with a certain amount of litter in the litter bag, place them in the field, then collect a subset of litter bag once every a few weeks, get dry weight, calculate the dry weight remaining in comparison with the initial amount. The data usually can be fit by first-order decay curve. The Changzhang synthesized nearly 300 data sets from 70 studies all over the world. His study found that this simple equation fit almost all data sets very well. Farmers often incorporate straw into soil. Andong Chai synthesized more than 16,000 data sets of straw decomposition for 6 types of straws. All of the data sets follow the donor pool dominated transfer equation. Now let's look at another carbon cycle process, which is soil organic carbon decomposition. SOC decomposition is usually studied by soil incubation. Basically, researchers collect the soil from field, put it in jars for a period of time. Researchers collect the gas sample once a while to measure the amount of carbon released from soil sample. Data are usually plotted by cumulative CO2 released on the y-axis with time on x-axis. Almost all data follow a similar pattern. This pattern also can be well described by donor pool-dominated carbon transfer. Christina Schidel tried to fit the data of soil decomposition with 1, 2, and 3 pool models. She found that 2 or 3 pool models works well for soil carbon decomposition. Christina synthesized more than 120 data sets from permafrost regions. Xia synthesized nearly 400 data sets all over the world. Both of the studies showed that more than 500 data sets can all be well fit by 2 or 3 pool models. We add a symbol A to the equation to indicate the carbon transfer among the pool. That's the donor pool-dominated carbon transfer equation can work for soil carbon decomposition. In addition, Yuanhe Yang synthesized more than 124 studies with 2,400 data points of soil carbon dynamics along forest succession. During the secondary succession, some forests gain carbon, some lose carbon. In either case, carbon dynamics still can be described by the donor pool-dominated carbon transfer. So far, I have shown you data sets from 6 types of processes. Thousands of data sets all confirm a macroscopic patterns that the donor pool-dominated carbon transfer equation can adequately describe all carbon transfer processes. The donor pool-dominated carbon transfer is one of the 4 fundamental properties that governs dynamics of the land carbon cycle. The other 3 properties are photosynthesis as the primary carbon influx pathway, compartmentalization of a carbon process into plant, litter, and soil, the first-order kinetics of carbon transfer from donor pool. Among the 4 properties, the donor pool-dominated carbon transfer is the most important in determining the trajectory of a land carbon cycle. If this property is altered, carbon cycle would not behave as we have observed in the real world. The 4 properties fundamentally characterize the internal process of a land carbon cycle. The internal process drives the land carbon cycle to converge toward some attractor. This is the reason why the places like Manhattan in New York City would become deciduous forest if a human disturbance was removed. This convergence is applied to almost all places on the Earth. Active research has been going on to examine properties of first-order kinetics, especially in relationship with microbial decomposition of soil organic carbon. Microbial physiology and other traits are surely important in catalyzing decomposition of soil organic matter and should be incorporated into Earth system models. To make the microbial-based models are useful for predicting real-world carbon cycle dynamics, those models may need to be constrained by the macroscopic pattern observed from thousands of data. The good news is that the 4 properties of the land carbon cycle are all well represented in a model as long as the model uses so-called pool and flux structures. In this structure, we use a pool to represent different carbon compartments, fluxes to represent carbon transfer among compartments. For this structure, we need one balance equations to trace how much carbon get into one pool and how much carbon leave the pool. For example, the leaf pool X1 receives carbon from photosynthesis partitioned to the leaves and lose carbon by senescence. Thus, we need one equation to calculate the amount of carbon from photosynthesis and the amount of carbon losing to the litterfall. When a model have 8 pools, we need 8 carbon balance equations to track the carbon movement. If a model have 500 pools like CLM5, we need 500 equations to track a carbon movement. About 20 years ago, when I first worked on this type of model, I realized that we can use a matrix equation to summarize all those carbon balance equations, no matter how many pools a model has. Once a model is converted to a matrix equation, it appears quite simple, a first-order differential equation. As I will discuss later, the equation actually is not that simple, as it represented a non-autonomous system. With this unified matrix equation, we can explore general property of carbon models. That's what we call the matrix approach. We are not the first group to use matrix models to describe the carbon cycle. Scientists use the matrix model to represent the carbon cycle in Earth system as early as 1958. What we did is to take the matrix expression to unify the land carbon cycle model, enable data assimilation, develop a theoretical framework to guide carbon research. For example, we have converted 4 versions of a community land model, CLM, into a matrix equation. The latest version of CLM, which is CLM5, uses nearly 450 pools to describe carbon movement and another 450 pools to describe the nitrogen cycle. Chris Liu has converted the CLM carbon-nitrogen cycles into 4 matrix equations. 2 for vegetation carbon and nitrogen cycle, 2 for soil carbon and nitrogen cycle. Once converted, the matrix equation makes CLM more modular, easy diagnosed, and computationally more efficient for spin-up. Here is a detailed matrix equation for soil carbon cycle in CLM 4.5, to which CLM 5's soil carbon cycle modules is similar. In the low right corner is the schematic diagram from Charlie Coben to illustrate the carbon process over multiple soil layers. Yuanyuan Huang converted this schematic diagram to a pool flux structure in the upper right corner. The matrix equation has 3 items: the carbon input and plant partitioning, carbon transfers and release, and the vertical movement. The dimension of a matrix equation is 70 by 70 pools. Transfer matrix A, for example, is a 7 by 7 block matrix. Each element of a block matrix is a 10 by 10 matrix, and the vertical movement matrix include carbon transferring 1 up adjacent layer and 1 down adjacent layer. We have converted nearly 20 models into a matrix equation. 8 of them was converted in last 2 training courses. Carlos Sierra's group from Max Planck Institute for Biogeochemistry in Germany have converted about 10 nonlinear microbial models into metric equations. Well, we argue that almost all the land carbon cycle model can be converted into a metric equation. The general equation is mathematically extremely simple. A paradox arises. How can such a simple equation represent extremely complex phenomena of carbon cycle observed in the real world? To explore this paradox, I organized a workshop in 2012 sponsored by U.S. National Institute for Mathematical and Biological Synthesis, NIMBIOS. We invited 20 applied mathematicians and 20 ecologists. I presented this paradox to the workshop participants. In first couple of days, it was very difficult to convince this group about this issue. Many ecologists say that ecosystems are complex, cannot be described by such a simple equation. They urged me to re-examine this mathematical expression. I told them that we have examined thousands of data sets to verify the equation. Applied mathematicians told me that this equation is too simple to be interesting enough for them to do any research with. They suggested me to add a nonlinear term in the equation. I told them that if a nonlinear term is added to equation, it no longer describes carbon cycle. I was very stubborn. I kept telling them this paradox. After 1.5 days, Jim Cushing, an applied mathematician from University of Arizona, said to me, "Ichi, the system you are studying is probably a non-autonomous system." At that time, I didn't know the word. I Googled it. Wikipedia explained that non-autonomous system is a branch of mathematics and study dynamical system with input and the parameter being time-dependent. This metric equation indeed has its input and the parameter being time-dependent. With this new knowledge, I organized a working group to study non-autonomous system, sponsored by U.S. NIMBIOS again. The working group consists of a few applied mathematicians and a few ecologists. One of the group members, Martin Rasmussen, a professor from Imperial College London, has co-authored 2 books on non-autonomous system. He taught us a lot about how to study non-autonomous system. We worked together for four times over 3 years and then gained a few key findings. For example, we found that nonlinear model of soil carbon decomposition generate damping oscillative responses to small perturbation. In addition, the equilibrium pool size of little or soil carbon is insensitive to carbon input in a nonlinear model. We also identified a mathematical foundation through proof of a theorem on exponential stability to explain observed convergence of land carbon cycle. It is because the land carbon cycle satisfies the 3 conditions. The first one is that there is always carbon to leave any individual pool. Second, there are either no carbon flow pathway or some amount of carbon moving from one pool to another pool. Third, carbon existing in one pool is either all go to other pools or some going to other pools or the rest being lost by respiration. Actually, the carols and plot the exponential stability in the lower panel to indicate this exponential stability concept of a non-autonomous system. This concept of exponential stability can be translated to understand the predictive carbon cycle. Given one type of forcing, patterns of carbon cycle dynamics are usually highly predictable. For example, periodical climate forcing over seasons usually influence the carbon cycle system to generate periodicity in carbon fluxes. Similarly, when fire disturbance events generate a pulse release of carbon from land to the atmosphere, followed by gradual recovery. Global change factors such as rising atmospheric CO2 concentration and warming usually generate a gradual but directional change in carbon cycle process. Shift in fire regime usually lead to disequilibrium in carbon cycle, and ecosystem state change, for example, and the land use change from forest to cropland usually results in disruptive change in carbon processes. Although many carbon cycle processes are highly predictable, the 5 categories of external forcing variables are superimposed on each other to influence the carbon cycle dynamic, and then generate a complex phenomena. This is why we observe the complex phenomena of carbon cycle dynamic in real world. Behind the complex phenomena is a relatively simple dynamic equation to govern the trajectory of a carbon cycle. It is well known that the carbon cycle dynamic at a steady state can be described by 2 terms, carbon input and residence time. The products of 2 terms determine the carbon storage capacity. To quantify dynamic disequilibrium in response to directional climate change, we need a 3rd term to represent transient dynamic of the land carbon cycle. The working group was working very hard. We derived a variety of mathematical formulations on transient dynamic of a carbon cycle. One day we came up with a 3rd term described the disequilibrium of a land carbon cycle. The original derivation was very complex. After a few rounds of reorganization, now we can explain the mathematical derivation in a very simple way. Basically, we can time each term of the equation by inverse matrix A, C, K, reorganize the equation to get the 2nd equation, and get the transient dynamic x equal to tau E times ut minus potential carbon storage. The first part of the right side of the equation is the steady state carbon storage capacity. The 2nd part is the carbon storage potential, which represents the disequilibrium term of a carbon cycle. In the coming 5 units of training, we will show you how the matrix approach can unify land carbon cycle models, accelerate spin-up, offer new analyticals for model diagnostics, and help data assimilation. Please take a few quizzes regarding these lectures. Thank you very much for your listening.